This is the first video of chapter 7 about Alkyne's reaction. It's going to be the second video of the entire chapter. In the first video, we already talked about nomenclature. So this is the second video, but the first video talking about reactions of alkynes. Now in this video, we're going to talk about electrophilic addition of alkynes, particularly adding halogens to the triple bond. Now, there are two small type of reactions in this video. One is shown as on the slide on the screen right now. We're going to try to add HX to the triple bond. X here stands for halogens. That could be fluorine, chlorine, bromine, and iodine. Now, of course, the chloride HCl and the HBr are more popular used than HF and HI. This is very similar to the electrophilic addition to double bonds in the last chapter, which means this is going to be our Markovnikov's addition. Now, of course, the true bonds, there are two pi bonds. Every addition of HX to it will open up one of the pi bonds to add X and H to one of each two carbons. And with the remaining double bonds, further addition can be carried out with excess of HX. So therefore, there are potentially first addition and the second addition. Now this kind of second addition can be controlled. Now each addition will require at least one equivalent of HX. So if you only add one equivalent HX, the reaction will stop at the first addition. You only add a second addition, excess of HX, the second addition will happen. The mechanism of this reaction can be seen as this. The electrophilic attack starts from one of the pi bond or a pair of pi electrons. So that's why you see the curved arrow starts from, the tail of the curved arrow starts from one of this bond, goes to the hydrogen. At the same time, the bond between the hydrogen and the chloride, in this case, or could be any halogen, breaks, in which the chlorine will take both electrons away. So this will take one equivalent HCl to undergo this so-called nucleophilic addition. The result of this nucleophilic addition is this carbocation intermediate. Now the same rationale can be implemented here, which is when you have more alkyl substituents on this carbocation, which will help to stabilize this positive charge intermediate, which will result into as one of the major products. And that's basically what Markovnikov's rule is about. So in this case, you can see this triple bond, one of the carbon is a terminal carbon with only a hydrogen substitute attached to it. The R group here stands for any hydrocarbons more than just hydrogen. Therefore, between these two carbons, the one on the left attached to R group can stabilize this positive charge better, which will be resulting into a major intermediate with a positive charge on this carbon, which also means the hydrogen in HCl will be bonded to the one with hydrogen only. Now with this positive charge carbon, or so-called a carbocation, the chloride, which was a result of the first step, will now do the second step to do nucleophilic attack to this carbocation, or in other words, the chloride will provide a pair electron to form a bond with this carbon, which will result into the chlorine attached to this carbon, or this hydrogen attached to the other carbon with hydrogen. And that's what we mean by Markovnikov's rule. The chlorine will be added to the more substituted carbon. The hydrogen will be added to the less substituted carbon. And of course, the triple bond turns into a double bond. Now, you might be wondering why does the double bond does not compete with the triple bond in this case if you have only one equivalent HCl when you have both triple bond and double bond presented at the same time? Well, that's because the halogen substituted alkene, which is the product of first addition, is less active than the alkyne. So in the presence of a triple bond, the HCl will be always preferred to react with the triple bond instead of the double bond. Therefore, if you only add one equivalent HCl, which will always give you the major product of addition to the triple bond, and instead reacting with double bond. The double bond will only react after all the triple bonds are consumed or all the triple bonds are exhausted by the HCl, and you still have more HCl, then this HCl will start reacting with double bond. Now, if you do have the excess or more than one equivalent HCl, then the second addition will start happen. Now, again, this is when all the triple bonds has been exhausted and you still have excess of HCl. Now, similar to what we learned in chapter 6, this is the exact same thing going to happen to the double bond, which is going to be result into a Markovnikov addition. This double bond, or specifically the pi bond of the double bond, start doing nucleophilic attack, pick up one of the hydrogen, result into a carbocation and a negative charge chloride. Again, this carbocation will be easier or happier to be on the carbon with substituents on it, and the hydrogen will be added to the carbon with hydrogens on it. And then the chloride will be bonded to this carbocation, which will result into a compound with one carbon with two halides attached to the same carbon, whereas the other carbon will just be bonded with a lot of hydrogens. Because of two consecutive steps of Markovnikov addition, we're going to have both chlorides added to the same carbon, or so-called germanyl dihalide. Dihalide meaning both halides are in the same molecule. Germanyl dihalide meaning both halides, in this case chlorides, are attached to the same carbon. Now, in this case, we're showing you an example of internal alkyne with substance on both carbons. Then, because of the equivalence of substance, these two carbons are not going to be selectively reacted with HX, which means you're going to have 50% of chance the halide will be attached to one carbon, and 50% chance the halide will be attached to or added to the other carbon. Now, of course, because of lack of selectivity, you're going to result the first addition into two products. You can see here one product with a double bond halide on one carbon, and the other one is with double bond halide on the other carbon. Now, between these two products, there's no preference in this case. But if you have two equivalent HX, which meaning you are able to do the second addition or second time addition to both products, then they will be selective. So with the first addition, the product on the left, when the second addition happens, the halide will be preferred to add it towards the carbon with the more substance, and the hydrogen will be added towards the carbon with the less substance. Therefore, you're going to form a germanyl halide with both halide on the carbon, on the same carbon. The other product will be the same. With two equivalent halide, after first addition, you're going to form half of the product to be on the right. With this product, first addition product, the second addition product will be again forming a germanyl halide, but this case, both halides are on the other carbon of the original triple bond. So when you have a term internal alkynes, both with carbons with substance on it, you will have a mixture of two products, either with one addition or with second addition. The next way of adding the halogens will be addition of Cl2 or Br2 instead of HCl or HBr. So this will be fairly straightforward. if you recall what we have done in chapter 6 with double bonds, both halides, either chloride or bromide, will be just added to the double bond. Now in this case, it's pretty much the same idea. So for example, if you conduct this experiment with any alkynes, regardless of whether it's an internal alkyne or terminal alkyne, with a 1 equivalent of Cl2 in the solvent of methylene chloride, or in other words, there's no presence of water, the chlorines will be added to each Cl2 will be split into 2 chlorines, and one of each will be added to one of the carbons, and the triple bonds will be turned into a double bond. The mechanism is fairly simple, or in other words, similar to what we learned in the double bond addition. The pi electron attached to the chlorine, and chlorine forms another bond with the other carbon, and the chlorine-chlorine bonds will be broken at the same time. These 3 electron moves simultaneously. And then with the formation of this triangle-shaped positive charged ion, the chloride will be attacking one or the other carbon. In this case, it makes no difference. They both will result into a chlorine attached to one carbon, chlorine attached to the other carbon. This addition is completely symmetrical. Now, this is only when you have only one equivalent Cl2. If you have excess of Cl2 or more than 2 equivalents of Cl2, then this resulting double bond will continue to react with second Cl through exact same mechanism, adding the second Cl to each carbon, which will result into an alkyne chain with 2 chlorides on each carbon, which results into total addition of 4 chlorides. Again, whether you have chlorines or with double bonds, or if you have 4 chlorines with no double bond, it depends on how many equivalents of Cl2 you added, and make sure there's no water, there's only CH2Cl2 or so-called methylene chloride as the solvent. Now here, let's take a look at a few examples of the reactions we'll be talking about. Now you might want to pause here quickly to see if you can come up with a product of each reaction. Now usually I would expect you to draw out the major product if there's one product to be favored, or draw out all products if you don't see any preference of any one of the product. The top one here, you can see the triple bonds here, you're adding 1 equivalent of HF. So in this case, both carbons are equally substituted. Now this branch does not show the preference on this carbon. To this carbon, on top carbon, it only has 1 substituent. So the choice will be HF, H and F will be added to the one or the other carbon, or F, H. There's no preference. Therefore, you're going to have 2 products. Now the way you draw this is going to be, try to maintain the main structure unchanged, such as this 4 carbon chain on top. Now down here you have a carbon, and you have 2 more carbons and another carbon. Now you are turning a triple bond into a double bond. Triple bond, of course, is linear with 180 degrees bond angle. But if you draw a linear double bond, that will be a little bit odd. So you would have a little banded. That's because of what double bond is. Now you're going to have 2 products. So I would at least draw 2 of them out. Now with one of them fluorine on one of the carbon, or fluorine on the other carbon. There's really no preference here. Now in this case, you might be wondering, Would the trans-cis or easy isomers be selective here? No. No need to worry. Easy or cis trans in this case, unless I specify it. Now the second one is adding one equivalent of Cl2 and in methylene chloride. So where the triple bond is, on each carbon, we're basically adding a chlorine to both carbons. So it's going to be a cyclohexane. The same thing. Now it's not going to be a linear double bond. It's going to be a double bond forming some angle, and then continue to next carbon, which is part of the cyclopentane. Now on each carbon, you're going to bond to a chlorine. And here you have to understand with only one equivalent, you're only adding Cl2 or two chlorines to the molecule. The double bond is changed to, the triple bond, now it's changed to double bond. Now, next one, this is similar to the first one, but you're adding two equivalent HF. So you have to think about this. When the first addition happens, what's going to happen? Well, because this is an internal triple bond, meaning both carbons are equally substituted. In other words, there's no preference when you add one equivalent HF to it. It's not going to form a Markovnikov product. So the first product is going to be, the first addition is going to result into two products. Now here's where you want to draw how you draw the product. Now keep the carbon chains as they are, but change the triple bond into double bond and make sure you form an angle. And then this continues to the next carbon, which has a branched structure on it. And you're going to have two products. Now with these two products, one of them is going to attach to the F, and the other product, the other carbon attached to the F. Usually you don't have to show the hydrogen. Now with the second addition, with both products, they're going to turn into a different product. First one on the left, the second fluorine will be added to this more substituted carbon only. And the other product, the second fluorine, will be added to the one with the fluorine already, and the hydrogen on the other carbon. And that's going to result into so-called germinal dihalide, which you're going to keep the carbon chain unchanged, but the double bond is now gone. And where you have a fluorine already, you're going to have the second fluorine. And then the other product will be adding the second fluorine to the same carbon with the fluorine already. They'll keep the carbon chains unchanged. Now with one fluorine and the other fluorine. And the hydrogen will be added to the other carbon. And that's not going to be shown here. And you can see the double bond is gone. Now the last one, where the triple bond is, and you're adding two equivalents Br2. This one is going to only result into one product, and that's going to be open up all of the pi bonds and add as many chlorines as you can, which will be two chlorines on each. In other words, just copy the structure Now it's not going to be linear anymore. Try to bend an angle. This is where the triple bond used to be, but now it's going to be gone. On these two carbon, each one of them, you're going to add bromine. Bromine. That's the first addition. Second addition, another bromine, and then another bromine. And these are all the answers to the examples on the PowerPoint.